Log on, tune in, find out. Another good idea from Cambridge.
Jens Groth talking about ElGamal Ciphertext shuffles.
Thank you. Yes, so let me start a little with a different kind of problem. So here we have a tin can, right? And the question is, how do we open this tin can? One solution is to take a chisel and hammer, right? And hammer around the edges and eventually open it. And if you look at the history of tin cans, this was actually the preferred solution. I mean, cans came with instructions saying, you know, take a hammer, take a chisel, and hammer around the edges, and you open the can that way. Obviously, it's not a very practical solution, and nowadays we have much more efficient tools. I think you see this kind of pattern appearing quite frequently in cryptography as well, right? We have something, you know, that we would like to construct, maybe public key encryption scheme that's secure against chosen ciphertext attacks, right? And you have theoretical constructions where you, I don't know, if you look at the Dollar-Neora scheme, you would have to send something like a billion bits for each bit that you encrypted, right? So it's not something that you would like to use in practice, but eventually it got better, right? And now we have Kramer-Shoup encryption, for instance, but it's pretty efficient. I think you've seen the same thing in the history of multi-party computation, right? The first techniques all appeared almost 3 decades ago, and were hopelessly inefficient. And now we're finally getting to the point where we can start doing multi-party computation in real life. So this is a pattern that you see quite frequently. And I'll try to talk about this in the context of communication-efficient zero-knowledge proofs. Okay. So let me explain what that is. So a zero-knowledge argument, we have two parties, a prover and a verifier. And we have some kind of statement. So this statement might be, for instance, that the prover claims I'm Alice, right? And I know some kind of secret related to Alice's public key. Or the statement could be that, you know, I'm following a protocol correctly. Or could be anything else. Okay, and the prover has some kind of witness for this statement and would like to convince the verifier that this statement is true without revealing what is the witness. And for that, you can use a zero-knowledge argument. So it's a protocol where the prover and verifier sends messages back and forth, and in the end, hopefully the verifier says, yes, okay, this is okay. So there are two properties that we would like here. So the verifier would very much like this zero-knowledge argument to be sound. Basically that if the verifier is convinced, it's because the statement really is true. And the prover would like this protocol to be zero-knowledge, that the proof, this zero-knowledge proof, this zero-knowledge protocol, does not reveal anything except that the statement is true. So in particular, doesn't reveal the witness. Okay, so to summarize, I mean, we need 3 properties actually, right? We need completeness, which says that the prover can convince the verifier if the statement is true. Soundness, which says that it's impossible to convince the verifier if the statement is false. And zero knowledge, which says that you don't reveal anything except for the truth of the statement. Okay. And zero-knowledge proofs are used in all kinds of protocols. For instance, in multi-party computation protocols, where you want to prove that you're following the protocol correctly. Okay, so there are various parameters you could look at here. What is actually efficient? So you can look at the communication. How many bits does the prover and the verifier send back and forth? How much computation does the verifier use? How much computation does the prover use? Look at the number of rounds that you have to send messages back and forth. And depending on the setting, one parameter might be more important than the other ones. Okay. The setting I'm going to think about, my priority list will roughly be that I care most about the communication and the number of bits that you send back and forth, and then about the verifier's computation. I will also care a little bit about the prover's computation. I will not care that much about the number of rounds. Okay. This is partially motivated by the fact that you can use the future mirror heuristic sometimes to compute all the verifier's messages back. So if it's a public coin protocol where the verifier just picks a random message, sends it back, then you can actually compute those random messages with a cryptographic hash function. And this way you can remove all the interaction. So it doesn't matter so much how many rounds we have. And the prover's computation doesn't matter so much because you only compute the proof once, and then you can send it to different verifiers and they all verify it. Okay, so if we look at zero-knowledge proofs, okay, and the communication that was involved, then, you know, I mean, they were invented back in 85, and Groth, Mikhaili, and Victorson showed that you could do that for all of NP languages. So it's all very well known that we have zero-knowledge proofs. They were not particularly efficient. Schnorr gave some, as an example of some very efficient zero-knowledge proofs that you can use in practice, right? They work very well in the discrete logarithm setting. And if you look at these kind of proofs, then they all have communication which is linear or superlinear in the size of the statement, right? So if the statement X, they will have some kind of description in some number of bits, right? And the communication for all these proofs is linear or more in the size of the statement. So it's a natural question, can we do better than that? Can we do something that's more efficient? And Killian showed in '92 that you can actually get down to polylogarithmic communication complexity. So you can get something that's much, much smaller than statement in theory. But however, you don't want to implement Killian's protocol in practice because it uses probabilistically checkable proofs. These are these horribly complicated constructions. The prover complexity would, you know, go up and be something really horrible. There will be large constants involved, large polylogarithmic factors, and so forth. Something that you would definitely not want to do in practice. And what I'm going to talk about here is basically an attempt to take some of the ideas that you have in theory, okay, developed for, say, Killian's proofs, and trying to see if we can actually extract some of those ideas and get something practical out of it. Okay, so I'll try to talk about practical zero-knowledge arguments where there is very little communication. So it'll be square root of the statement size communication. Okay, so the problem I'm going to look at relates to anonymous broadcast. So we have here a bunch of senders, and they all have some message that they would like to broadcast to the world, but they would like to be anonymous. Okay, and the way you can do that is you can submit the messages to a mixnet in some secure manner, and then the mixnet will permute the messages and output them. And since the messages have been permuted in random order, then just from seeing the messages, you don't know who sent which message. So this is something that's used in voting, for instance, right? So you can imagine a voting scheme. People come, cast their secret votes, okay? They're mixed around, and the authorities output the votes in random order, and now they can start counting them. So if we look a bit more in detail of how could one construct a mixnet, basically three parts here. One question is, how do you submit your inputs to the mixnet? So there has to be some kind of secure protocol for that. Then you'll have to mix these inputs somehow, and then you'll have to output these messages. So the submission will basically take place this way. When you submit a message, you encrypt it with a public key for the mixnet and submit it to the mixnet. And then there'll be the mixing phase, which I'll get to in just a moment. And then the output of this mixing phase will be encryptions of the same messages, but in permuted order. And furthermore, the mixnet has also changed the randomness. Okay, so it's re-randomized these input ciphertexts to having some new randomness, and therefore you can't link output ciphertext to the input ciphertext. Okay, so now we've permuted and anonymized the inputs, and now in the end you'll have the mixnet would also have to do some kind of decryption operation for the ciphertext to get out the permuted plain texts. Okay, so this public key here that the mixed servers use is something they can generate jointly, and we would like that no single mixed server has a secret key. So it'll be some kind of secret shared secret key, because if any single mixed server had the secret key, then it could actually see what people were inputting and so forth. And we would like to have a strong level of security and prevent that. Okay. And the output then, well, when we actually get to the output phase, we have these permuted ciphertext that have been re-randomized. Then the mixed servers will corroborate and use the secret key to decrypt and get out the plain text. Okay. So this encryption scheme that we're going to use should be a homomorphic encryption scheme. It makes for an easy way to build mixed nets. Okay. So a homomorphic encryption scheme is one where you, well, if you have two ciphertext encrypting two plain text, you multiply those ciphertext, what you get is a new ciphertext that has the product of the plain text. And this is useful, particularly, so one special case of that is where you take a ciphertext and multiply it with a random encryption of 1. What you get is a new ciphertext that has the original plain text, but it has a new randomness. Okay, so one example could be ElGamal encryption, for instance. Okay. So now we're ready to build a mixed net. Okay, so we have the senders here. They have the messages that they would like to broadcast. We'll have a couple of mixed servers running the mixed net. And the way it works is that first they encrypt the messages, they submit that to the first mixed server. The mixed server permutes these ciphertexts according to some randomly chosen permutation, and then it re-encrypts. Then it sends it to the next mixed server, and the next mixed server also permutes the ciphertext and re-randomize them. And then we have finally the output, where we use some kind of threshold decryption algorithm with the mixed servers, and we get out the plain text in permuted order. Okay. So the reason we do this, this permutation, re-randomization many times is that no single mixed server is going to know what is the permutation, right? If you look at the first mixed server, it knows what its own permutation is, but it doesn't know the permutation of the next mixed server. So even if there's one of the mixed servers that is corrupt and dishonest, it still has no clue how to link senders to the output messages. Okay. So all this is good. So this process of permuting ciphertext and re-randomizing them is called a shuffle. Okay, and what we have here is that each mixed server acts in sequence and shuffles the ciphertext coming from the previous mixed server. And if all the mixed servers follow the protocol, and at least one of them keeps the permutation on it secret, then, and the encryption scheme is semantically secure, then we have a mixed net which gives you anonymity. Okay, you cannot link the output plain text to the input ciphertext. Now the problem here is, what if we have a corrupt mixed server? What if one of them is not honest? Okay, so suppose we have these senders and encrypt them messages. We send them to the first mixed server. First mixed server permutes a little, and then it replaces one of the ciphertexts. Okay, and you're not going to detect this because it's all encrypted, right? I mean, for you it just looks like any other random ciphertext. You can't see whether it took a malicious ciphertext and inserted instead of one of the original ciphertexts. So now that would go to the next mixed server, which may be very honest, but that would just permute those ciphertexts and re-randomize them. And what we get out is now that we have the first mixed server has inserted a new plain text into the mix, replaced one of the plain texts. So we would like to avoid this problem, And the solution is that you can use zero-knowledge arguments to avoid this problem. Okay, so if we have zero-knowledge arguments, then what we would require is that each mixed server gives the zero-knowledge argument that it has shuffled correctly. Okay, so the first mixed server would have to give a zero-knowledge argument that what it did was actually honest, it followed the protocol. And the soundness of the zero-knowledge argument will guarantee now that no message has changed. Okay, so the input plaintext are the same as the output plaintexts from the first mixed server. And then it would go, the protocol would go on, right? The next mixed server would also give a zero-knowledge argument. And the honest mixed server is happy as well because this is a zero-knowledge argument. So even if it gives this zero-knowledge argument, it doesn't reveal what is the permutation it's using. And we decrypt, and now we are guaranteed that the plaintexts are actually the same ones as the senders put into the system. Okay, so the question is, how do you build an efficient zero-knowledge argument for a shuffle here? This is really the most expensive operation in typical mixed nets. Okay, and it's been something that really, I mean, for realistic parameter sizes would, you know, if you go back some years, it would be something that could take hours to do. Okay, if you had an election with, say, 100,000 voters, you know, it could, you know, easily take an hour or two to do this kind of zero-knowledge argument. Okay, so the central operation here is this shuffle, right, where you permute, you take some input ciphertext, you permute them, and then you re-randomize them. And you get some output. And we would like to build a zero-knowledge argument. So the statement is this input ciphertext, output ciphertext, and the prover would like to convince the verifier that this is a correct shuffle. And the prover, of course, knows the permutation and it knows the re-randomization factors that have been used. But it would not like to reveal that to the verifier. So therefore, they will engage in a zero-knowledge argument, and well, hopefully they'll get the verifier to accept, right? And the verifier is happy because of the soundness, which guarantees that the shuffle is correct. That's what the zero-knowledge argument proves. And the prover is happy because the zero-knowledge property guarantees that the permutation remains secret. Yes, the verifier gets to see both the input and output ciphertext. So the typical way, so I'm omitting some details here. I think the typical way is you would imagine you have basically a bulletin board. Okay, so everything actually happens in public, so to speak. So you have senders submitting their input ciphertext, just broadcasting them to the world. This is my ciphertext, this is my ciphertext, and so forth. Then the first server will take all these input ciphertext and do the shuffle and publish its output. Okay, so permuted and re-randomized ciphertext. Then the next server will take that, permute and re-randomize and publish again. So everything here is actually public.
If the original ciphertext are public, doesn't that defeat the purpose of the shuffle?
Well, if you have the, I mean, so you're not trying to hide that somebody is submitting something to the mixnet, right? But you're trying to hide what they are submitting. And since it's encrypted what they submit, then it's secret which kind of plaintext they're putting into the mixnet.
The question is, who is the verifier?
Right, okay. So it could be anybody who's interested in checking on a mixed server. So typically it would, for instance, be the other mixed servers that would do this, ask for this zero-knowledge argument before they even proceed with the mixnet and go to the next step in the protocol. But you could also imagine having independent third parties that want to verify that everything in this mixnet has been done correctly.
But if there are multiple parties verifying, you envision that they will use some join randomness, or
Um,
they will run.
they could do that. I think that the typical application of this would actually be you use a Fiat-Chimie heuristic to make it non-interactive. So the prover, the mixed server, will compute all the challenges from the verify using a cryptographic hash function, and then it will just output the entire zero knowledge argument in one go, and publish that for the entire world to see, so anybody can come along and check if they want to check it.
Will you be able to do that with your? You're going to do a zero knowledge with not too many, like with communication, communication complexity.
Yes.
Will that also be non-interactive? Can you make it?
It could be made into non-interactive in this way, exactly, yes. So what I'll present is a public coin protocol, so you could compute all these challenges from the verify using a cryptographic hash function. Yes. Okay, so let me get to the more technical part. Okay, so how to construct this zero knowledge argument. Okay, so remember I want this to be something that has very low communication. And for that, I'm going to use a tool called commitments. So a commitment is a way that we can commit to a value, okay? So in this particular case here, we'll want a commitment scheme where we can commit to a vector of values, okay? Integers modulo some prime q, say, okay? And we'll call, so there will be some, you'll take the values that you commit to and you'll take some randomness as well, okay? And combined we call that for the opening of the commitment. Okay, so the commitment scheme has a public key, a commitment key CK, okay, and then it takes the values and the randomness as input and outputs some bit string, which is a commitment. And we would like this commitment scheme to be computationally binding, okay, so it's not feasible for an adversary to find two different openings of the same commitment. So if you have a commitment, you can think of the adversary would know at most one possible way to open this commitment. And also it should be perfectly hiding. It should reveal no information whatsoever about these values, A1 up to AN. And finally, I would like this commitment scheme to be length reducing, which means that the output, this capital A here, is a bit string which is much shorter than all the combined length of the inputs. Okay. So I'll give you an example on the next slide here. Okay, so one example would be the Peterson commitment scheme, okay, where you take the values you want to commit to and so take them as exponents to some group elements which are part of the public key, and then you multiply with some other groupment raised to some randomness R. Okay, so no matter how many elements you're committing to, what you get out is just one group element. Okay, so that's the length reducing property, that you can commit to an entire vector of elements with just one group element. And also it's easy to see that this is perfectly hiding, right? Because of this h to the r factor, it's a completely random group element you get, no matter what the values you're committing to are. And then you can show that if you could actually find two different openings of such a commitment scheme, then you could break the discrete logarithm problem. Final property that this has is that it's homomorphic. So in other words, if we have commitment to one vector or commitment to another vector, multiply those commitments together, we get a commitment to the sum of the vectors. Okay? And this is really cool because now we can do operations that are verifiable to the verifier, but where we're actually sending very little communication, right? If I send two commitments to the verifier can himself compute the product, right? And it knows that now it has a new commitment that contains the sum of these vectors. So in some sense, this sees very little communication, but it's doing operations on vectors of elements. It's actually doing a lot of computation in parallel. So, and I'll show how this can be used in a zero knowledge argument. Okay, so the challenge here is that we have public keys for the encryption scheme, for the commitment scheme. We have the input ciphertext and output ciphertext of the shuffle. And the prover knows the permutation and the re-randomization factors, right? And now wants to convince the verifier that it has permuted the input ciphertext and re-randomized them. So and it will work like this. So the prover first commits to the permutation. Okay. So it will commit to the values 1 through n in permuted order, and that will be a commitment to the permutation. After this, the verifier will pick a random value x and send it to the prover. So this is the verifier's challenge to the prover. Now the prover will construct a new commitment, b, which contains powers of x, so x to 1 through x to n, okay, in permuted order, using the same permutation. Prover will give a zero-knowledge argument that a and b contains respectively 1 through n and powers of x power to respectively 1 to power n, okay, and that they have been permuted in the same way. And I'm going to skip the details of that zero-knowledge argument. Prover will also give a zero-knowledge argument that there's some randomness rho such that this product of the output ciphertext raised to the bi values, whatever they are, so these are the b1, b2, and so up to bn, okay, is the same as the product of the input ciphertext raised to powers of x, okay? And the only difference between these two products may be some encryption of 1, okay? So what this means is that the plain text here raised to the bi's, okay, is the same as the plain text here raised to the x to the i's because of the homomorphic property of the encryption scheme. And this is just an encryption of 1, so that will cancel out. Okay, so what does this give us? So we have the zero-knowledge property because, well, the first commitment is perfectly hiding, so it doesn't reveal anything. And the second commitment is perfectly hiding, doesn't reveal anything. And then we have a zero-knowledge argument, which doesn't reveal anything. And then we have another zero-knowledge argument that doesn't reveal anything. Okay, so that's where we get the zero-knowledge property. Okay, so let's now argue that we have soundness here. Okay, so this multi-exponentiation argument that we do in the end shows that there exists a rho such that this equation here holds. And if we look inside, well, the bi's, they were x to the powers of x, right, in permuted order. So if we plug that in, then we have this product on the left side, and we just keep the right-hand side. Okay. And if you look at the plain texts, this is a homomorphic encryption scheme, that means that we have the plain text of the output ciphertext raised to permuted powers of x, and on the right-hand side we have plain text of the input ciphertext raised to powers of x, right? And this 1 here, that just cancels out. Okay, and with very high probability over x, this implies that these output plain texts are the same as the input plain text in permuted order. Okay, so it's easy to see that if this really holds, that the mi is permutation of the input plain text, plug that in here, then we see that we are taking product over the same things, just in permuted order, right? So that would work out. And if this doesn't hold for all I, then with very high probability of x, we would catch the prover here. This would not be possible for the prover to show. Okay, so that's the high-level idea. Now, the expensive part of this argument here is this multi-exponentiation argument. Okay, so I'll try to sketch the idea of how we build that. Okay, I'll just focus on soundness. I'll completely ignore zero-knowledge, which is easy and cheap to add anyway. And I'll also, for simplicity, assume that rho is 0, so you can kind of ignore this part here. Okay. I also want to notice that all this information here is public. Okay. The verifier knows the input ciphertext and it knows the challenge X. So it can compute this product here. So the question is basically just, so let's call this product here for C, right? And basically what we want to prove is that this product here to these output ciphertext raised to the secret committed BIs is the same as this C here. Okay, so let me use some notation. So this commitment B, I'll actually commit to B with many commitments. I'll pick M commitments. So and in each of those M commitments, I'll commit to N powers of X. Okay. So I'll assume here that capital N is the same as M times N. So I'll commit to column vectors. I'll arrange these powers of X as permuted powers of X as column vectors, M column vectors with N elements in each. And I'll arrange the ciphertext in an M times N matrix where I have N ciphertext in a row and I'll have M columns. And then I'll define a natural inner product, which says if we have a row vector of ciphertext and a column vector of exponents, then that's the natural inner product. And that simplifies what I'm trying to prove. I'm basically trying to prove that these rows here is taken to the power of a column vector like this product here is the same as C. Okay, so now I'm getting to the idea, which is taken from Hadamard code essentially, which is used in probabilistically checkable proofs. So let's look at this matrix here. And if you look at what we have on the diagonal, that's exactly this product here that we want to show is equal to C. Right? And the prover will compute that, and it will also compute the other diagonal products. So there are M minus N products up here, and there are M minus 1 products here. So there are two M minus 2 different diagonal products you can compute, and the prover will compute all of those and send them to the verifier. So the prover sends these to the verifier. The verifier picks a random challenge Z. Okay, and the prover will now open this product of commitments. Okay, so take all these M commitments and raise them to Z minus J powers. And the homomorphic properties of the commitment scheme show that this means that we get a commitment that contains this sum here. Okay, and now we can compute also products of these ciphertext raised to Zi powers. So these should be vectors actually. Okay, and what we get now is we can compute this C vector here raised to this B here, and doing a lot of computation, you get this is actually the same as these diagonal products, right? So you have C here, and then you have all these other diagonals. Let me just illustrate that on the next slide. Okay, so what we get is, so here we have the power, we take these commitments to different negative powers of Z's, right? So we get that here. And we have the vectors of ciphertext here, we take to positive powers of, that should be Z instead of X. And what we have down the diagonal is still the same thing as before, we have C. But now what we have for the other diagonal products is that now we have raised them to different powers of Z. Okay, so what does that give us? Okay, so now we have this sum here of these. That was one part of what the prover computed and revealed to the verifier. The prover reveals this B vector to the verifier. And well, this is public information. Everybody can compute this vector of ciphertext. And what the verifier checked was that this power of c raised to this b vector is the same as this product over here. Okay, so you can do all these computations. And what you see is that, well, if you look at the z to the power 0 term, okay, so z to the power 0, that's exactly when I is equal to j. What we have then is the product of the ci's to the bi's. And that's what we wanted to get, right? And then we have all the other things, okay? But now they have all been raised to different powers of z. Okay, so if we have to z to the 0 term, that's exactly what we want to get out. That's c, and all the other things have been raised to different powers of z. Okay, and the probability over a randomly chosen challenge z that this should hold true is negligible, unless indeed c is the same as the product of the ci's raised to the bi's, which is what we wanted to prove. Okay, so that's kind of the very short sketch of what is going on and how you can use these techniques from probabilistically checkable proofs to get an efficient argument. So now let's see if it actually is efficient. Okay, does it hold what I promised? Okay, so if we look at the communication, then the prover sends 2m ciphertext and a vector of elements here. So that's 2m ciphertext and n elements. Okay. So if m and n are chosen to be roughly the square root of this capital N, then we actually have square root communication complexity. And if we look at the verifier's computation, well, you'll have to do n exponentiations to compute this thing here. And this capital C was something that the verifier also spent n ciphertext to exponentiations to compute. And then it has to compute these things here in the end. That's 2m exponentiations. But m is small. That's roughly the square root of capital N. So we ignore that. So overall, this is very little work for the verifier. Something that's linear number of exponentiations. Okay. So we have now very little communication and some small linear amount of computation for the verifier. So far, so good. What about the prover? And here we have a bit of a problem, right? Because the prover has to compute these products here, okay, these multi-exponentiation products. And well, the trivial way would be to compute the matrix and then compute the products. But the computation involved in that would actually be m times n exponentiations, because each of these entries in the matrix is a product of two vectors, which has n elements each, so that's n exponentiations for each of them, and you're doing m squared of those, so you end up with m squared times n exponentiations. And if m is roughly the square root of capital N, then this is something that's really expensive. So you don't want to do that. And this is kind of where we kind of started now. Now we go into engineering mode. Can we somehow do this more efficiently? And it turns out that yes, you can do that. You don't have to compute the entire matrix. You can actually kind of get to these diagonal products in a different way. You can use a fast Fourier transform to do that. Have to skip the details. I don't have time to explain how that is done, but you can do that, and you get complexity which, instead of growing linearly in m, it grows logarithmically in m. So you get an n log m complexity here. And this gives you also just a constant number of rounds, okay? Or an alternative is you can use an interactive technique. Basically, you can use a technique that you can spend a couple of extra rounds of interaction, and you can reduce the cost with roughly a factor 2 or factor 4. so some constant factor. So if you do that a logarithmic number of times, then you have reduced it down to linear computation complexity. Okay, so the upshot of this is then we get two protocols. So here I put a table with all the different shuffles I could find. There's been quite a lot of work in this area. And you can see that most of it since 2001 has been kind of linear complexity. Okay, and now we actually have something which has very little communication, sublinear communication. If you choose m to be roughly equal to n, then you have square root of the statement size here. And very little computation for the verifier. And then you can trade off, do you want to have low round complexity or do you want to have low complexity for the prover? Okay, so we thought this is great. Let's start implementing this stuff. And there you get into all kinds of other obstacles. So asymptotically, so we wanted to get some kind of constant round solution. And asymptotically, the fast Fourier transform is the best for that. But it actually takes a long time before the asymptotics kick in. Okay? So if you compare that with the multiplication of integers, right, then also fast Fourier transform techniques are the fastest. You can actually multiply large integers in time roughly n log n, okay? But the cutoff is, I think, around 10,000 bits or something like that before it actually pays off. And before you get to that barrier, other techniques are more efficient. They are not theoretically the most efficient, but in practice, the most efficient. Okay, there are other issues as well. I mean, in theory, the cost for the fast Fourier transform would be n log n. But it turns out that it doesn't work well with multi-exponentiation techniques that you also want to use. And multi-exponentiation techniques typically give you a log n saving. So actually the cost is not just log n, it's log squared n. And again, if you're a theoretician, you say, oh, whatever, it's just a polylogarithmic factor. But if you're doing something practical, then logarithmic factors do matter, right? I mean, if n is 1,000, then log n is 10, right? And if you're paying log square n, then we're paying a factor of 100. That does matter. So it turned out that actually the real world, we found that the interaction technique worked best. And the reason is that for practical choices of m and n, the interaction does come kind of for free. Okay, so remember there were two zero-knowledge arguments. Okay, one was that this a and b commitments had permutations of the respectively integers 1 through n and powers of x. Okay, and that argument has a round complexity of 9 rounds. Okay, so we'll have to spend 9 rounds anyway. And the multi-exponentiation argument has less rounds. So actually we have 4 rounds. So that multi-exponentiation argument is 5 rounds. So there are kind of 4 rounds left. And you can use them for free and use this interactive technique. And for each pair of rounds, you can get a factor 4 reduction in the complexity for the prover. Okay? So we do that for 2 rounds, get a factor 4. We do that for 2 more rounds, we get another factor 4. So now we have factor 16. Okay? And then we do the multi-exponentiation argument with the Thum-Cook techniques to get another factor 4 for a total of a factor 64. Okay? Which we get essentially for free and with very low cost for the prover. Okay, so we did that. We implemented it with 100,000 ciphertexts and m equal to 64. We chose 1024-bit for the prime p. So we worked in the group ZP star, and we worked in a subgroup of 160 bits. I'm not recommending those parameters for practical use, but the reason we did that was to compare with previous work that had used these parameters. And we get a complexity which is, well, 9 rounds of interaction, 12n exponentiations for the prover, 4n exponentiations for the verifier, and communication cost of 0.7 megabytes. So this should be compared with the statement size, right, which, if I remember correctly, for these parameters, it ends up with something like 50 megabytes, was it? Yeah. Okay. And our implementation shows that this is something that you can easily do on even a weak laptop, right? So 91 seconds for the prover and 18 seconds for the verifier. And then we looked at other implementations. So if you compare with work from Furukawa et al., they had an implementation where they did all kinds of optimizations. And they ended up with a 66 megabyte communication and about 300 seconds of computation. And we definitely beat that. We have much smaller communication. Douglas, he's going to talk about verificatum in a couple of days. We implemented that scheme on the same computer, and we got so on the same machine about 300 seconds as well for the communication for the prover and the verifier, and about 37.7 megabytes. I know that NEF also has an implementation because I had a company called Vote Here that used this in voting protocols and tried to sell it, but I don't have any performance estimates for their system. So we get, very significant reduction of the communication involved. We also get a reduction in the computation involved, but then one has to be careful about these measures because it depends on the machine and the code and the optimizations and so forth. So I think depending on the implementation, it could easily go the other way as well, I expect. Okay, so let me conclude. What I really wanted to talk about was that you sometimes have some really nice properties in theory, and there's actually quite a lot of work to go from theory to something that's practical, right? So we took ideas from probabilistically checkable proofs, Hadamard codes. We took fast Fourier transform techniques, Tom Cook techniques that are used in polynomial multiplication and so forth, and all this kind of work together and pull these things together to get something that was practical. Okay, so you may ask, is it practical? And I think the answer is yes, that's something that you can easily run. And then I think the final thing is, okay, so I'm claiming here that it's practical. I want to distinguish between practical and practice, okay? Because one thing is, what we have built now is kind of a component of a mixnet, right? And we've shown that that's practical and that's really fast and so forth, right? But there's obviously still some way to go until we really have it in practice, right? So I guess one possible path one could imagine was, you insert that in a mixnet. So maybe we could put it into Douglas's verificatum mixnet. And then, hopefully we'll get people to use Douglas's mixnet with our shuffle argument and so forth. So there's still some way to go until we actually have it out there and people using it. Okay, thank you.
Time for one quick question.
I have a question. Is it a proof of knowledge or an argument of knowledge?
Yes.
Yeah, you can extract all the randomness.
Yes.
Yeah. Any other quick questions?
I guess since Douglas is here as well, it's next question. So the first question I wanted was to ask you was what Douglas just asked. Why was the technical difference between calling it an argument rather than a proof? So I wasn't quite sure I got the answer.
Yes. So the difference between a zero-knowledge proof and a zero-knowledge argument is in the soundness. So a zero-knowledge proof is one where the soundness is unconditional. Okay, so no matter how strong the adversary is, you can't convince the verifier. The zero-knowledge argument is one where a polynomial time adversary cannot falsely convince a verifier. And all these things have to be arguments when there's sublinear communication complexity. It's simply not possible to create a sublinear communication complexity proof. It has to be an argument.
just ask one quick question?
Why don't we take it offline? Since we're already a few minutes behind. Let's thank the speaker again.